Okay, wrapping up Module 2. You'll be working on your quiz this week as well with all the various contents for Module 2. We'll just spend a little bit of time on circular motion. And again, circular motion we use if we're cycling in a velodrome. Even if the velodrome is not circular, we can model parts of the curves as circles. We use it for orbits. And again, the orbits quite often are elliptical, but we can model them with circles. So circular motion is actually really quite useful. Anything where we're using a centrifuge or anything like that is quite helpful as well. So just a reminder of what we know about circles. The circumference is pi times the diameter. That's way too many digits of pi. 3.14159 is plenty for most normal purposes. There's been some really interesting stuff recently where 15 digits of pi is enough to calculate the circumference of a circle as big as our solar system to within a couple of inches. So 15 digits, and there's more than 15 digits there. So it's very, very precise if you use a lot of digits, but even 3.14 is fine for most everyday purposes. The diameter is twice the radius, or the radius is half the diameter. So the circumference is 2 pi times the radius. So if you measure around the outside of a circle, 2 pi times the radius. We could talk about the area being pi r squared as well, but the area is much less relevant for our perspective. The radius, if you think about it, if you start at the x-axis and sweep out one full circle with the radius, that'll be 360 degrees or 2 pi radians. And we need to be fairly comfortable switching between degrees and radians, making sure our calculator's on the right mode and so on. So working across those systems hopefully is helpful. When something's moving in a circle at constant speed, it's constantly accelerating. You'll remember some weeks ago when we talked about velocity, we said that either if the speed changes, it goes faster or slower, or the direction changes, it's a change of velocity. And that Newton's laws tell us that a change of velocity requires an acceleration, or is an acceleration really. When we change velocity, we are accelerating kind of by definition. So that acceleration is given by v squared over r, the velocity that it's doing around the circle divided by the radius of the circle. And the direction of the acceleration is toward the center. So this probably helps a little bit, although it's a little bit small in spots. So we've got our circle, we've got our radius. The velocity of the circle, of the particle traveling in a circle is always a tangent to the circle. So you can see it heading off at v meters per second as a tangent to the circle. And you can imagine that vector, which is its velocity vector, is continually rotating around the circle and continually changing its direction as it goes. So the velocity vector keeps changing its direction, and because it's changing its direction, there's an acceleration, and the acceleration is v squared over r, which you saw on the previous slide. So it doesn't matter if this one's a tiny bit tiny. We can also express it in terms of angular velocity. So rather than the velocity of the particle at an instantaneous time, the angular velocity of the radius itself spinning around. And if we do that, it changes from a equals v squared over r to a equals r omega, where omega is the rotational velocity in radians per second. So that one is also helpful to have. It might be new to you, but we'll try and work, as I say, across those spaces. Unless you have like a radar gun or something, if you are spinning a stone around your head on a string, measuring its velocity is going to be quite tricky. Even if you're doing it at a very consistent pace, actually measuring the velocity of that stone at the end of the string is not going to be so easy. So it might be easier to measure the period. How long is each complete rotation taking? So if the period t measured in seconds is whatever it happens to be, in that time, it's traveled 2 pi r meters, right? Because that's one complete circumference, 2 pi r meters. So from velocity equals distance over time, the distance is 2 pi r and the time is t seconds. So the velocity is 2 pi r over t. that make sense? So you've got a way of calculating that velocity from the period rather than having to measure it directly, which, as I say, unless you have the advantages of the police and a radar camera, might be a bit tricky. So we can substitute that into the A equals V squared over R, because we just had an expression for V. If we substitute that in, square it out and reorganize it, the top is the one where we haven't quite cancelled everything out. So the bottom equation is the one to look at. So the acceleration can also be expressed as 4 pi squared R over t squared. So in terms of the period rather than in terms of the velocity. It's another way to express that centripetal acceleration. You will have probably heard in everyday life of centrifugal force, or centrifugal, people pronounce it differently. So for example, if you put a couple of inches of water in a bucket and spin it in a vertical, again, magical disappearing hand trick. If you spin it in a vertical circle, you can spin it without losing the water because you've got that force. Now, we tend to call that centrifugal force. We tend to talk about centrifuges that you can put your blood into and spin out the different fractions and so on. But really, what we should be talking about is centripetal force. The force is acting towards the center of the circle, not outwards. It appears as though it's acting outwards because we're continuously trying to accelerate that water toward the center. Does that make sense? The water is in the bucket. We're trying to accelerate it toward the center by pulling on the handle. And so it's accelerating toward the center continuously. And the direction of the force and the acceleration are in the same direction. That's Newton's second law. So the acceleration is actually toward the center, not away from the center. Oh, there is a great XKCD comic with James Bond about centrifugal and centripetal force. It's worth looking up. XKCD, centrifugal force. It's kind of cool. So we can use Newton's second law, F equals ma, and we've got a couple of expressions for what A might be. So we've got A equals V squared over R. So if we sub V squared over R in for A, we get F equals mv squared over R. Or we've got A equals R omega, F equals mr omega. Or we've got the one using the period. F equals ma again, F equals m times 4 pi squared R over t squared. So we've got a number of ways of calculating that centripetal force. And again, we'll spend some time calculating and working through that and just thinking about circular motion in general and how it works, what we can use it for, how it's actually helpful in calculating things like the friction of a car going around a bend of a particular radius and so on.